Got one more minute. Don't forget, I also gave you the equation. You should go ahead and 5 roots from the equation.
So confusing, x squared part.
X squared, I believe it's x minus or plus 1 squared.
Yeah, I'm saying like eventually, it would be x squared, but I don't think I
I
can
would figure that.
multiple of x squared.
Are you talking about multiplicities or degree? I will say it might help if you think about it in factored form. Huh?
Can you take mine?
Yes. I have yours. Alright, I'm about to collect. This is a quick understanding check to see what we retain. I will go over a couple of these details. Oh, yeah, time to collect. Alright, we'll do this again on Monday. Not gonna spend forever here, but I do wanna look at a couple of these. It looks like we're struggling with domain and range. For some of us, yes? When I say domain, what do I mean? The set of all what?
This way.
This way, the set of all inputs, set of all x's. Alright? When I look at this graph, and this is what you need to keep in mind. When I look at this graph right here, is it ever going to quit going to the left?
No.
Is it ever going to quit going to the right? So what is the lowest x value? Negative infinity. And the maximum x value? Positive infinity. When I talk about range though, am I talking about x values at all now? No. Talking about y. And that's what I was trying to tell you, Gracie. Domain is one of the values, range is the other. So when I'm talking about range, I don't give a dump about the x values. The only thing that matters is the y. And if you checked, both of these y values I believe were the same because of symmetry. What was the y value? Yeah, something ugly. It's okay if you just went 1 or 2 decimal places. Negative 1 point what? 1,3. And that is the lowest y value that you have. You gotta put a bracket or parenthesis with it. What's the difference?
Bracket means you can't multiply by oh, I thought, never mind.
Bracket stop.
Bracket means you, well, kind of. You stop with both. A bracket means you can equal that number or that you include that number.
I thought it was the other one.
Notice how the infinities have the parentheses because you cannot equal them. So then what is the maximum y value? Positive infinity. We good there? So hopefully that was a good little recap. Again, you'll have a chance to do this again. Did we have any questions? Okay, really quickly, because I realized I never actually talked about this. So maximum, that's singular. Maxima, because this comes from a Latin root.
Teachers, please excuse this interruption. Any senior that signed up for cap and gown pictures, those have been postponed and will be taken at a later date.
Okay. Maxima is plural. Okay. It comes from a Latin root, which is why it works like that. It's like alumnus and alumna, or alumnum versus alumni. Okay. So it's a Latin root. Same thing with minimum becomes minima for plural. So that's why you see the A there. But were we able to identify the max and min pretty well? Just looking at these sections.
Oh, I think it's the top part.
Yeah,
Huh?
is it?
The top part was like, I think it's the maximum for the maximum for the little hump thing. They had it.
Okay, you need to be careful about how you do it though. So remember, you have to hit maximum.
Yeah, that's what I
Yeah,
I think you get like X.
So-
6,
Hold on.
3.
Hold on. Analyze. Maximum.
And then you get like X.
Okay.
And then the whole number.
Okay, you're talking about that 1.26 e to the negative 7? Something like, it may not be exactly that, but Is that what you're talking about with the x? Okay, we talked about this a little bit before. Remember, when it's e to the negative 7, that's scientific notation. Which, that means I'm literally going to, a negative exponent is repeated division, so I'm dividing by 10 7 times. That's going to move my decimal 7 times. What is that really close to? And what is that x value supposed to be? 0. That's just calculator rounding errors. That's the point, 0, comma 2. That's your maximum, huh? It's scientific notation. The calculator doesn't do the times 10 to a power, it just does the e. Why? I have no idea. It's probably some computer programming thing someone did forever ago.
I didn't know how to write it.
So remember, we don't write that point. What is the maximum value?
I did the little line on the side and it zoomed out the whole graph.
But that's because, remember, we talked about a relative maximum. I'm not talking about the maximum for the whole graph. We'll talk about that later. Whenever we talk about a relative maximum or minimum, it is the maximum and minimum for that section. That is a maximum for that section. And so I had to go right around here. If I actually went too far to the right, it was going to pick up one of these points because that's higher than that point.
Yeah, I kinda just.
But we only want that relative maximum. You good back there?
I just cut my back and it was really loud.
Oh, gotcha. So, does anyone remember how we would write this relative maximum though? When we say the maximum, are we talking about the x value or the y value? Okay, so we would say the relative maximum is 2 when x equals 0. That's all you do. The relative maximum is 2 when x equals 0, because the value is 2. And you would do a similar thing with the minimum. We good? Okay. 1.3, what was the degree of this? 3. Okay. The degree was in fact 3. No, that's wrong one. And then we have our, well, notice the multiplicities are on the next one, but, I don't know. Yeah, what is the degree? Degree 3. Because how many factors did we have? 3. No way. You sure about that? So, that's all you could see. That's my bad. Let me show you this again.
It was 4.
It's 4. Look at your graph. This is why I knew that we made a mistake. How many roots do we have?
4.
Oh, so what's the degree?
4.
4. Remember, the degree is the same as the number of roots.
I got a question. How do you know the roots? When we had, you know when we did yesterday when we did the little subtraction, the 1 thing, how you supposed to be looking at that or you supposed to be looking at?
Subtracting the 1.
When
When you talking about when I'm looking for my multiplicity
Yeah.
of the roots, we'll look at that in a second. But like all the degree is the highest power, which every linear factor has a degree of 1. So if I have 4 linear factors, the degree is 4. Each linear factor has a degree of 1. But also remember, and I just said this, the degree always matches the number of what? Roots, right? Which remember, that's that fundamental theorem of algebra. Every polynomial of degree n has exactly n complex roots. We good on that idea? Alright, so what are the roots and what is the multiplicity? So I will say I saw a lot of us setting it equal to 0, and you can totally do that, but if you look again at this equation, you can actually figure out the roots without doing any extra work. It was 1/2 times, well, f of x equals 1/2 times x plus 2 times x plus 1 times x minus 1 times x minus 2. Think about your factored form. What is the root here? -2. What is the root here? Here? And here? Now, this is what you were thinking about Well, Shannon, if I'm looking for a root, it's the same as saying 0 equals 1/2 times x plus 2 times x plus 1, yada yada yada. That's the zero product property that we can now use, where we say 0 is equal to x plus 2. Because to get a 0, I had to multiply by a 0. Is that what you're talking about when you say subtract earlier? Yeah. So that's when I'm trying to figure out my roots. But again, do you need to set equal to 0 in order to identify roots based on what we did with factored form before? No. If it makes you feel more comfortable, go for it. We good with that idea? So what is the multiplicity of each one of these roots? 1. Okay? The multiplicity for each of these roots is 1. And that's in contrast to, this is why I had the second question on here. So I will point out, in this graph, documents, how many x-intercepts do we actually have here? 2. But how many roots do we have to have? 3. Does anyone know, looking at the graph, which one of these is going to be called a double root, or a root with a multiplicity of 2? Okay? Look at the graph though. How do we know that's going to be a double root? Remember, what is this root? X equals what? 1. So that's here. So what's happening when I have a double root? I mean, is it crossing all the way through the x-axis? What is it doing? It's touching it and then bouncing off of it. That's when we have those double roots. It's going to look like that.
So if they're separated, like if that equation, instead of saying x plus 1, had another x minus 1, would we say,
Say that one more time.
like on that equation right there, everyone, if it was x minus 1 instead of x plus 1, like there were 2 of them that said x minus 1, would that be like the same thing as that?
It says x minus 1. I'm confused.
No, over here, look at the second one, or there's the little plus in between them. You put a minus on the x plus 1.
Right here?
Yeah, so if there were 2 with the
Yes.
same thing, we
Yes.
need a 0 for each of them, but then
Right.
you said that the, what was it, the multiplicity or something?
It'd be a multiplicity of 2. Because it's the same root.
Mhm.
And that's the whole point of a multiplicity, is if I wouldn't have this root anymore, I would have this root, but how many times do I have it? So the multiplicity is 2. Do you have a question?
So if it doesn't go through it, it's 2.
Sometimes.
Right.
This is a good question, okay? Look at it now. It doesn't go through, does it? It just touches. But what's the multiplicity? 4. We actually started to look at this yesterday. With even multiplicities, it's going to touch and then go away. Which means with odd multiplicities, it's going to go through. So I could have done, and this will look interesting, notice that x plus 2 is linear, but if I make that x plus 2 cubed, you see how it kind of squiggles through there? It's very brief, but it squiggles through, just like that cubic function we started to talk about. And so we'll look at that again today. That's a good question, though. All right, let's move. Hopefully that was a good little review so that we can be better prepared for today. We got to get through this so odd I can't even, all about end behavior. Definitely got to get through activity 2.1 and then hopefully get through that third part. I'm going to introduce literacy for all for maybe 10 minutes, but we got some math to learn since I won't see y'all on Friday. So we started briefly looking at this so odd I can't even yesterday. Notice, and this is what I was talking about, DJ, right here. So y equals x squared, you see how it touches and then bounces away? Same thing here with y equals x to the 4th. Notice though it's a little bit flatter down here at the bottom. Similar thing with y equals x to the 6th. Yes, sir?
Do you know that we don't have school tomorrow?
Yes.
Okay.
Yeah, did you go work on this, you're like,
Friday.
Friday.
I know, I never planned on seeing y'all tomorrow, so that's not losing a day of instruction.
Okay, well, you just
Losing the day on Friday.
The way you were talking to me.
No, I very clearly talked about Veterans Day yesterday, but by the time y'all left, I didn't know that I wouldn't see you Friday either. Yeah, but I won't see y'all. And so I do want y'all to notice with y equals x, right? See how it goes through, but it starts to get that curve in there, and that curve flattens out more through the origin in the middle, right? Yeah, that's a great question. 160 something? Maybe? I was so far off. It's M1-196. Thank you, Lexi. Yikes. Okay. So I believe we already did part A, correct?
Yeah.
Yes. Did we state any observations or patterns that we noticed? Yeah, if it's even, and I don't think we talked about it, and it's not necessarily a parabola. I will say a parabola is only quadratic, but I will say that if it's an odd, or if it's an even, it looks like a parabola, right? It has similar behavior. And that may be something you want to say, right? That if it's an even power function, then it looks similar to a parabola. Go ahead. Right? The only real difference is, again, what's happening in the middle near what we would call the vertex. It's getting what? Wider, flatter, right?
Can you spell squiggle?
So like for here,
SQUIGGL.
Is
Yeah.
there a word for that? Or is it
Yeah,
just
it's
a-
a word.
are you talking about through here?
That sounds
Yeah,
like
it's a
a
word.
yeah.
Not that I'm aware of. That's not to say that there's not, right? So the power function is even, then it looks similar to a parabola, just flatter in the middle, or let's call it flatter at the, I'm gonna call it vertex. It's not quite a vertex, kind of is. And so if the power function is odd, it looks similar to, I would just call it to a linear or cubic.
If we wrote squiggle on the text, would we take off the word?
Yes. I won't take all, but you could not earn a 6. Because the best way, the most apt way to describe it is it looks like a cubic. That, right? I wouldn't necessarily look just like a linear because that's a straight line, but it continues to look more and more like the cubic. Again, just flattens out in the middle there. It's called a point of inflection.
I think squiggle sounds more professional.
Yeah, 100%, right? That's 1000% true. Yeah, I'm just gonna say it looks more similar to a linear cubic, okay? So, what we're going to do is we're going to use this to talk about end behavior, okay? One of the major parts of a polynomial function that we analyze is end behavior. What do you think I mean by end behavior?
Where it stops.
But does it ever stop?
The overall.
So like, let's say I have this function. I'm just going to make something up real quick. Let's say I have this. That's a function, right? Notice, does it ever stop? No. So what could I possibly mean by the end?
Ends on the graph that we see.
Yeah, like how it changed from where it was and what.
So one thing I want to point out is, you say what we see on the graph, or what we can see, but is that the end of that function? No. But can I make a prediction about where it's going to end? So I'm going to pause on that for a second. So DJ, is the middle the end? Definitely not, right? So look up here, what do you see that would indicate the end of that function? The arrows. The graph on your calculator won't have the arrows, but you know that it's going to keep going in that direction, correct? These arrows indicate the end behavior. And so we're going to get into more of that in a second. Yeah, let's go ahead and just, actually, no. I do want to answer this question really quickly right here. So please notice when we come back to this, the end behavior is talking about the arrows, but I do want to address the middle here. Why does the graph flatten as the degree increases? So you remember how in the center we kept talking about how it flattens? I believe that this chart is already in your book, correct? Filled out? Okay, so I want you to look at that chart. Why is it flattening out in the center there? So look at your odd degree first. Focus in this section. Why is it flattening out?
They're the same in the front part. Yeah, so it just stays there and it's like, ooh, higher.
But look at the numbers. Why is it doing that?
Negative.
I want you to notice, like I have x cubed here, right? When I do negative 1/2 cubed, I get negative 1/8. But if I do, sorry, yes, that's what I meant to do. If I do negative 1/2 to the 5th, I get negative 1 divided by 32. Tell me, which of those is closer to 0? 1 divided by 8 is closer to 0 than 1 divided by 32? Pick up your calculator, do 1 divided by 8. Just do the 1 divided by 8, because I'm just trying to figure out which one's closer to 0. Hit Control and then Enter, get the decimal for me. And then do the same thing for 1 divided by 32.
0.125.
Okay, and then give me that 1 divided by 32. So which one's closer to 0? 1 divided by 32. So when I divide, you got to remember this, we're dividing by a bigger number. If I divide by a bigger number, I'm going to get closer to 0. Right? So whereas the cubic function, so here's, let's say this is negative 1/2. Negative, we'll just make this up. There's negative 1/8 right here. Alright? Nope, that's positive 1/8. I want negative 1/8. So that point would be somewhere around here. But that's my cubic. When I look at my quintic, we'll talk more about that later, that's negative 1 divided by 32. Do you see how it's already closer to 0? So when it's coming up and through, it's going to flatten out more and then increase. Whereas the cubic isn't going to flatten out as much because I'm raising it to a smaller power. Right? So it's the idea that when I multiply a number less than 1 repeatedly, it gets closer to 0 more quickly. Okay? And so what I want you to see about this is it's about the nature of the exponent. We can't just say, oh, look at the graph shows it to me. The graph matches the equation. The equation and the graph are intimately connected and they are very much related. So when it's between negative 1 and 1, right? When a number between negative 1 and 1 is raised to a higher power, it gets closer to 0, or the, let's say the result, the product. Gets closer to 0. So higher degrees have outputs closer to 0. It's not just looking at a graph and saying, oh, that's what I see. That graph matches the equation. A number between negative 1 and 1 is raised to a higher power. That product gets closer to 0, so higher degrees have outputs closer to 0. Specifically, right, between negative 1 and 1. And that's why it's flattened out. It's close to 0 between that negative 1 and 1. And you see that result within the evens as well. Okay? Now, when you get greater than 1, or less than -1, you see how these higher powers are going to grow much more quickly? That's why it's much steeper on the ends as well. So, between -1 and 1, it's closer to 0, so it flattens out. Greater than 1 and less than -1, it's growing more quickly, because 2 raised to the 6, it's 64, right? I'm repeatedly multiplying by 2 each time. That's what's happening there in the center versus the outside. Again, the big thing I want you to get from this is that graph is not random. It's the result of substituting these x values in and getting y values out. It's you substituting those x values in and getting the y values out. Those things are connected to each other. Now, this part, number 2, is what really matters for me. This is going to be the big deal. Observe the behavior of each function, right? On either side of 0 using the tables and the graphs. Describe the behavior of a function of odd degree on either side of 0. So remember how this arrow is what's going to the right. So let me ask you this. Is that ever going to quit going to the right? So at the far right, which is where the end would be, what would the x value be? Infinity. As x approaches infinity. That's the end behavior, because the furthest to the right. Now I'm not quite done there, because I still need to know about y, but end behavior looks at the far left and right of the function. I would make that note so that you understand where we're getting this idea of end behavior from. It is important to notice that the end behavior looks at the far left and far right of that function. Is it? Grayson, don't fall asleep on me.
Seems to work. You know?
He was dozing off.
My grandpa said in the army he learned to sleep with his eyes open just so he like could just sleep in general, and they never called him. He would just be
That's
sitting there
impressive. So Jada, as x is going towards infinity, right? So as x continues to the right, what is my y doing? Right? As my x is going to the right, going towards that positive infinity, based on this, what is my y doing? It's going up. Is it ever going to stop going up? So what is y approaching? Yeah. That's it. That is what we need to recognize. It's not what's in the middle. It's about those arrows, right? So as our x goes to the right, okay, so x is going to infinity in this case. What's my y doing? Oh, it's going up, so it's going to infinity.
Is it an actual number? Or
No. It's a concept. You can't reach infinity, so it's not an actual number.
like to infinity and beyond.
Except we can't go beyond infinity because
Can't get there in the first place.
exactly.
But I'm confused on the.
100%. Broke me when I
Maybe
found out.
maybe he meant it as a concept too, and y'all didn't get it.
So Gracie,
Is the egg? I was confused because I thought X was the arrow going that way.
x is which direction?
right.
Left and right. So that's why I say as x is going towards infinity. As x goes to the right, what is my y doing? It's going up to positive infinity.
So are they gonna make us do the other side too? Like
So-
That's a good question. Is this the entire end behavior of that function? No, that's only the right hand end behavior.
So is
Well,
y is going to
ain't
the left.
ain't they both gonna be infinity anyway, because as long as it goes to the right and the more it goes up, they all gonna go to the
Close.
Isn't the one-
Here, as x goes towards, notice, you said we're going to the left this time, right? Or correct? Well, but also, what is x approaching?
Infinity.
Negative.
Which one is it? Infinity or negative infinity? That's an important distinction. Well, remember, this is the right hand in behavior, x goes towards infinity, but as we go to the left hand in behavior, x is going towards negative infinity.
And then what y is negative infinity too?
Y would be approaching negative infinity. Look at the arrow. It's going to continue going to the left and it's going to continue going down. So as x goes towards negative infinity, y is going towards negative infinity. Does that make sense?
Yeah.
We good? Why not, Jada? Okay. So I do want to point out, if you look back at the graphs, is that true for just the cubic function, or is that true for all of our odd degree functions?
True for
It's true for all the odd degrees.
Yeah, they're gonna stop.
Is it true for all the evens?
Well, what that, that not, the one right there, the x, the y equals 4x, won't that not be true, because it don't have no negative going down.
So, x to the fourth, what about x squared? It's not going down either, is it? So, what we have to do, and I'll go ahead and tell you this, there are ways to figure it out without the graph. We're behind on time, so I'm not going to stress about it without the graph. Just use your graphs, right? So, notice we have to have a right hand in behavior. We also have to have a left hand in behavior. But notice if I were to do an even one, it might look something like this. So will I still have as x goes to infinity?
Yeah, it's
Actually, I'm going to do this. Can I start with as x goes to negative infinity? Can I flip it and do the negative infinity first for x? As long as I indicate that's the left hand in behavior, that's fine, right? So as x goes towards negative infinity, what is my y going towards?
positive.
Y is now going towards positive infinity.